for inviting me. It's great to be here. So, report on some ongoing work with Heluani. So we already posted one paper on the archive, but we're still trying to understand these structures that we discovered. And so I'm going to present these structures that we kind of stumbled upon in the course of our work on physics, and they are closely related to Vertex algebras. They are also different, and I'll try to explain what are the differences and what are some new features that appear, especially the connection with the three-dimensional hyperbolic geometry. So, first of all, what about Vertex algebras? So this is a big topic. I'll just focus on the features that I need to discuss for this talk. So, roughly speaking, one can start with V, a vector space, say over the complex numbers. And the basic structure is encoded into a map. It's called a state fields correspondence that to elements of V assigns endomorphisms of V parameterized by formal distributions in the formal variable Z. So to a vector A, I'm going to associate something that is called a field. It's an endomorphism that depends on this parameter Z, and you can expand it out into power series. If you want this, the choice of labeling may seem strange, but it's traditional. Okay, so this is the basic piece of structures, and the axioms that we want these structures to satisfy, at least the most important ones that I'm going to be concerned with today. The first one is that if I take now this family of endomorphisms parameterized by as coefficients of this power series, and I act on a vector V of my vector space, what I get is an element is a formal Laurent series with coefficients in V. Okay. So a priori it would be just a formal power series in Z and Z inverse, but I actually wanted to have poles of only 5 orders, so we stop at some point. And the second piece of axiom that we need is that what we want is not just any endomorphism, but we want them to be almost commutative. In the traditional terminology is that we want these operators to be local. So locality. So the most efficient way probably of packaging the information of this data is to require that if I have two such operators, and I compose them, so one that depends on a formal parameter W, then I compose with another one that depends on a formal parameter Z, and then I do the opposite things in opposite order. Then the result is not quite 0, and that would be too strong of a requirement, but it's 0 after I multiply by sufficiently high power of Z minus tau. So 0 for n large enough. So this is one way of stating this axiom, this almost commutativity. But let me expand a little bit on this, because this is one point that I want to discuss later. So one way of rephrasing what locality means to prime is in terms of matrix elements. So let's pick an element of the dual vector space, and V is again an element of my vector space. Then I can look at the tautological pairing V with, say, AZ BW V. Okay? so this is an element of the field of this field. For Lorentz series with variable W with coefficients that are formal power series with parameter Z. And so this we wanted to so we can the axioms are going to say that we want this to be convergent. Convergent power series for the region where Z is greater than the absolute value of Z is greater than the absolute value of W, and this can be analytically continued. To C star cross C star minus the diagonal with poles on the diagonal as opposed to more complicated singularities, such that the restriction to the region where W is greater, absolute value of W is greater or equal than Z, then this is given by a different convergent expression that is the one where the two operators are exchanged. Okay, so in other words, there is one actual function or distribution that lives on this space, and then we have two different ways of writing it, expanded out as a power series, one in this region and one in this region. Okay, so this may seem a little bit strange of the structure if it's the first time you see it, and the reason well, it turns out that this is not strange. There are many important examples in mathematics of these structures, but the reason why people started to look at these things originally was from physics. So the idea is that so vertex algebras model, one possible mathematical model for, strictly speaking, 1/2 of the chiral part of the sigma model. What is the sigma model is the physical system attached to the space of maps from C star or from a circle, in this case C star, so we're thinking in terms of the Lagrangian formalism, to some manifold M, which is called the target space. And so the parameter Z is a coordinate on this copy of C star. So the picture is like this. I have my circle, then it extends a little bit to make a copy of C star. I can think it as a cylinder that maps into my manifold M. And then I can study all possible configurations of these maps. And this, as a cylinder, represents the possible evolution of a circle-like object. So these things are important, for example, in string theory, where one thinks that ordinary particles are replaced by strings, little circles that propagate in some ambient space. And so it's important to get a description, mathematically precise description of these things. And it turns out that vertex algebra are pretty good at this. capturing this information. In particular, if I want to model my sigma model with a target that is simply connected, then vertex algebra do a very good job. And what we get is vertex algebra that I'll note like this. And this is basically the, just for short, I call it the Carl-Deram complex. So this is slightly cheating. So the Carl-Deram complex is actually a sheaf of vertex algebra over the target manifold M. But when you take global sections, you get a nice vertex algebra. And this is the vertex algebra. And this captures essentially a good deal of the physics of the model, if the manifold is simply connected. If the manifold is not simply connected, then the situation is a little bit more complicated. So there is one case which is well understood, which is the case of torus. So here gamma is some lattice. And so I can look at the corresponding torus. And in this case, I can also construct a vertex algebra, Vm. In this case, I emphasize the dependence on the lattice, gamma. And this is an example of what is known as a lattice vertex algebra. Which is a particular type of vertex algebras, in which the basic fields in this lattice vertex algebra are labeled by elements of the lattice and the dual lattice. So they're of this form. Alpha is the notation that I use, alpha x z, where alpha is in the lattice gamma, and beta star x w, say, where beta star is in the dual lattice. And then if I want to calculate expression like this, what I get is that if I take alpha x star z and I pair it with beta star xw, what I get is log of z minus w times the product of alpha and beta star. This is the product with respect to the tautological pairing on gamma plus gamma star. So, plus. So just take an element of gamma star and applies to an element of gamma. Okay, so you see that this is, even though these are basic fields that we use to construct the lattice vertex algebra, this is not, doesn't look good as of now, because we have a log here, and it's not satisfying the locality axiom that we had before. There's no way of killing log by multiplying by some power of z minus w. However, there is a way out, and I can exponentiate my fields, and so I can, so alpha x z and beta star xw, not good field. They're not well defined because of the indeterminacy in the log, and not local in the sense that we described before. However, I can exponentiate them and look at expressions like this. And then what I get is something like this. And then I do get something like, there are some issues of sign that I'm sweeping under the rug, but this is basically what we get. So in this case, we get a nice vertex algebra, and it is generated by these things. Of course, then there are more fields that one can obtain by taking, say, derivatives of these basic things, but this is all you need to reconstruct everything. And so, in this case, we have a theorem that was originally proved by Kapustin and Orlov. Various versions of this, of course, were in the physics literature for many years, but the first mathematical rigorous proof that I know is of Kapustin and Orlov, and more recently with Heluani, we found a different proof, more along the lines that I described here. And it says that, so vertex algebra isomorphism between two lattice vertex algebras arising in this way are in one-to-one correspondence with isometries. Gamma plus gamma star with tautological pairing to gamma prime plus gamma prime star with their own tautological pairing. Okay, so the lattice doubled in this sense. The lattice together with its double, together with the tautological pairing, is controlling essentially all of the vertex algebra. And we have this nice correspondence. And this can be enhanced further. So, can you prove the statement? And so, for example, we can add what are known as generalized complex structures. Which include complex structure, symplectic structure, non-commutative deformations, and other structure, let's say just complex and symplectic here, on the torus. And again, these structures depends really on the lattice. Okay. And this corresponds to enhancing the structure of vertex algebra into the structure of super vertex algebras. So you have extra, the vector space now becomes graded, and you have extra isomorphisms, extra symmetries that corresponds on the lattice side to these generalized complex structures. This is not terribly important for today, but just that there's more to this picture. Okay, so we can construct vertex algebras out of sigma models with target torus. And then what about vertex algebra coming from other non-simply connected manifolds? Particularly, it turns out that it's tricky, the case where the fundamental group is infinite and non-commutative. So, twisted case. So if the fundamental group of my target is non-commutative, things are more complicated. Or more interesting, depending on your point of view. So let's focus on a very simple case. So a case where M is the Heisenberg nilmanifold. What is Heisenberg nilmanifold? This is the quotient of the real Heisenberg group by its integer subgroup. And here, for any ring A, I call the Heisenberg group of A the group of 3 by 3 upper triangular matrices with one along the diagonal, such that X, Y, and Z are in A. Okay, so I can do it for the real numbers. The subgroup of the integers, X on the left, take the quotient. Turns out this is a compact manifold that you can think as a three-dimensional manifold that you can think in two ways, either as a circle vibration over a torus or as a torus vibration over a circle. So clearly the fundamental group here is the integer Heisenberg group is non-commutative. And when with Bermuda we first started looking at these things, we realized that even in physics, it wasn't very clear what the sigma model with target such a space should be. To our surprise, it's not very different from a torus. It's a circle vibration over a torus. Still, there was no clear picture of what should happen when the fact that the fundamental group is non-trivial is taken into account. And we found out that there is a good reason for this type of sigma models to be somehow forgotten from the literature, is that in fact they don't give rise to a vertex algebra, contrary to what one might have expected based on the experience of the simply connected case and the torus case. And so this is what I want to discuss, the type of structure that arises in the study of the sigma model we target these manifolds. So the first step to understand this is to listen to the physicist and observe that so according to physics, so the sigma model, the study of maps from a cylinder to this manifold M, will target this manifold, is equivalent, and equivalence is what is provided by a certain symmetry of string theory, which is called T-duality, or twistor T-duality in this case, is equivalent to a sigma model with target torus gamma tensor R over gamma, where here gamma is a three-dimensional lattice, but not just a naked torus. It has an extra piece of data, which is a three-form, an integer three-form on the torus. So this can be thought of as as a magnetic background for the strings propagating into it. But let's just say that there is this extra data, this tree form, that needs to be taken into account. I'll say how we can use it. So, if this was just a torus, as I explained before, we would construct the vertex algebra was basic fields are labeled by gamma direct sum with its dual. However, here things are more complicated because of the presence of this H. So what we should be doing instead is look at an extension of gamma by gamma star. Let's call it lambda. That is depending on this H. So it works like this. Have alpha and say alpha 1 and beta star 1. So this is an element in gamma, this is an element in gamma star. And I want to describe the group operation. So I have another alpha 2 and beta 2 star. So what I get is alpha 1 plus alpha 2, and then beta 1 plus beta 1 star plus beta 2 star. So far I'm not surprised. But then I am twisting this by adding 1/2 of H applied to alpha 1 and alpha 2. And then I leave the third entry empty so that I get an element of the dual lattice. So this is a free two-step important group, very much like the Heisenberg group, it's just this is of rank 6. And this is the type of group that is really controlling my new structure that is going to be this generalization of the vertex algebra instead of just the naked direct sum of gamma and gamma star. So, okay, so what does this structure look like? Well, the basic fields are still going to be labeled by lambda, which as a set is the same as gamma plus gamma star, just the group operation is different. And so they're still going to look like alpha x star z and beta star x w, say for alpha in gamma and beta star in gamma star. And in fact, if I pick one of these guys and one of these guys, and I look at the matrix element that corresponds to the corresponding fields, this is still going to be the same as before. So far, no surprise. So I still have that alpha x star z and beta star xw. This is still log of z minus w alpha beta star, where this is again a tautological pair. So it's exactly the same expression that I had before on the board. So here, there's nothing different here. But there is, so before this was all I needed to construct my vertex algebra. Here we have an extra piece of data that we need, and it's the following. So we have that, let me write it in the exponentiated form. So I have that I pick, say, E C, and I pair it with, P, as I had before, and I pair it with e to the alpha, x star z, and then I can pick e to the beta x star w, and e to the gamma as a vector that I'm applying these fields to, then this is e. But now instead of having the logarithm, I have another function which is the dilogarithm. So I have L W Z, and here I have again e to the alpha, e to the beta, e to the gamma. So L here, L of Z, is Rogers logarithm. Let me first write the expression. It's minus 1/2 Z log of 1 minus x over x plus log x over 1 minus x dx. It's Rogers logarithm. Sorry, I forgot the important piece. So here depends on h. So apply to alpha, beta, and gamma.
Okay, Marcus. On the left-hand side of T-duality, how is it independent of the h you take?
So the yes and no. So the particular way in which this is a circle vibration over a torus. So this is my M here. This is a circle vibration over my torus. This is my Heisenberg manifold. So the topological type of the circle vibration is specified by the Euler class of the bundle. And so, if this has Euler number 1 or minus 1, and so this is why here I get an H that would be here the basic volume element for this lattice. But if I pick the different Euler number, it would be multiplied by some integer. But it has to be integer. So only have this is a three-dimensional lattice. The third order powder only have an integer amount of choice, and this is the same integer amount of choice that I have. So yeah, so it's kind of surprising because usually T-duality is changing data of the same type, so topological data with topological data. But here we're exchanging topological data with algebraic data, I guess just 4. So this is what physicists tells us to do, and it can be made precise at the topological level. For example, you can show that the RAM complex here is naturally isomorphic to the twisted the RAM complex here. So there are many things that one can do, but this at the level of matching vertex algebras or vertex algebras-like structure, which is supposed to encode the whole thing, at the level, for example, of the theorem of Kapustin-Orlov that I mentioned before for tori, this was not understood before my work with removal. Any other question? So here we have now two pieces of structure involved. So one is the tautological pairing on gamma plus gamma star. But now I have this more general matrix elements that involve this strange looking function, the Rogers logarithm, and they depend on the twisting on the H, on this tree form that I have here that I'm using to pair alpha, beta, and gamma. So here, alpha, beta, and gamma are all in the actual lattice gamma. Like here I was pairing things in gamma and the gamma star. Here everything is happening in gamma. So it's really reflecting this new structure that we introduced this H here. Okay. So what can we say about this? First of all, let me say a couple of things about the logarithms. This is the definition. They satisfy some interesting identities. One of the simplest is this. If I take the Rogers logarithm of z plus Rogers logarithm of 1 minus z, this is Rogers logarithm of 1, which I think it's pi square over 6. This is identity due to Euler. And there's one other, well, there are several identities that are satisfied, but one that is particularly nice is the following. So this is called the pentagonal identity or 5 terms identity. So I get just the logarithm, I would stop here, but then it continues. So I have z minus cw over 1 minus cw plus L of w minus cw over 1 minus cw. And this is due to Abel. So this highly non-trivial functional equation that is satisfied by the logarithm. So let me leave it here for a second. I'll come back to it a little later. One other cool property of the logarithm is that it is related to three-dimensional hyperbolic geometry. So if I have three-dimensional upper of space, like so, and say that I have 4 points zi that are on the boundary hyperbolic upper of space. So they live like here. Z1, Z2, Z3, and Z4, I can construct the hyperbolic tetrahedron that has geodesic sides and vertices on the ZIs. So delta is the geodesic hyperbolic. Tetrahedron with vertices the ZIs. Okay. If I try to draw it, it would be a little bit messy, but you can imagine. So, of course, it wouldn't be possible for a Euclidean space to have an undegenerate tetrahedron with the vertices all on one plane, but in hyperbolic geometry it's possible. So maybe I'll draw a lower dimensional picture in the hyperbolic upper plane. Then you could have a triangle that looks like this. Okay, so you can imagine how the three-dimensional version is. Okay, so this is the this tetrahedron, and its volume, you can compute it as the imaginary part of the Rogers logarithm of the cross ratio. Yeah, and we have a very neat formula for calculating the volume. Okay, this also, let me leave it here for a second. The other point of view of the logarithm that I want to emphasize is as sections of line boundary. So just as the logarithm has monodromy as you go around 0, the dilogarithm has more complicated monodromy as you go around 0 and 1. And so there is a construction due to Deligne that goes as follows. There is L is a tautological C star bundle over C star cross C star, such that it restricts to a U1 bundle over U1 cross U1. And in that case, we wanted to be isomorphic to the Heisenberg nilmanifold. Okay, so or in other words, you can start with the Heisenberg nilmanifold and then you complexify all the circles to copies of C star. And so this gives you a C star bundle over C star to C star. So now you have sigma, a Riemann surface, and you have f and g that are functions from sigma to C star, non-vanishing holomorphic functions. So the Riemann surface has to be non-compact. Then what you can do is that you can construct a bundle L sub fg, say, on your Riemann surface, which is just the pullback of through f and g of the tautological bundle that you have on C star to C star. And this comes with equipped with the natural connection, and you can look at flat sections with this connection. And it turns out, it's an easy calculation, that if sigma is the projective line minus 3 points, say 0, 1, and infinity, and if I pick as my functions f, 1 minus z, and g to be z, then the logarithm Lz is a flat section of the bundle L1 minus z, z, Roger's logarithm. And so, using this interpretation, you can rediscover this type of identities. So, as in terms of isomorphism of line bundles. So, for example, Abel's identity becomes something like 1 minus z, z, tensor L of 1 minus w, w is isomorphic to 1 minus zw, zw, tensor L of 1 minus z minus zw over 1 minus zw, tensor tensor L of 1 minus w minus zw 1 minus zw. Okay, so you have a line bundle version of the identity. So when you pass to flat sections, you record. Okay, so now I have what I need to formulate my proposed generalization of the notion of vertex algebra that I started with. So remark. So this suggests a generalization of vertex algebras where so before, remember, I had an expression like this. The matrix element corresponding to these two operators, and the requirement was that I could extend it to a function on C star cross C star minus the diagonal with poles along the diagonal and so on. So this is no longer possible here, but what we can do is to require that this is a section of a line bundle, is a section of a line bundle over CP1 minus number of points. In our case, for the dilogarithm, we need 3 points squared, such that it converges over the region where Z is greater than W to this expression here, and over the region where W is greater than Z to dW AZ. Okay. So basically we are replacing functions that we had before with sections of line bundles. So it includes this possible monodromy that we obtain. So this is part of what we want. Well, so it turns out that for ordinary vertex algebras, the locality axiom formulated like this in terms of functions actually takes care of also of the associativity of the product and so on. So you can recover other desirable properties of the vertex algebra from just the localization axiom, the locality axiom. But here it's not so easy to recover those things if we were working with sections of line bundles instead of functions. So we have to require this extra structure like of associativity and so on in a slightly different way. And so this is the last thing that I wanted to discuss, the factorization structure. So in other words, so suppose that now I have 3 operators. You know, how do I associate them, for example? How do I do first product of 2 and then the other one? What requirements does this has to satisfy? So what we get is maybe I'll just write the formula here. So what we have is phi of e to say alpha 1 x star z1 e alpha 2 x star z2 e alpha 3 x star z3, and then say e to the alpha 4. Then this is the product. This nice formula. The product of e to the alpha 1, e to the alpha I removed, brought over the i's, e to the alpha 4 times e to the to the, say, let me write it in this way so that it's more clear. Delta I, then I'll explain in a second what this is, times h of alpha 1, alpha I removed, alpha 4, so I'm firing only 3 of these at each time. And what is delta I? Delta I is the volume of the hyperbolic tetrahedron, which is just another way of encoding the dilogarithm, with vertices at 0, z1, zi removed, z3, and infinity. So, what is this telling us? So, it's telling us the following. So now I'm adding one more field. So I have now 3 fields. So I'm thinking in the following way. So I have 0 here, z1, z2, z3, and infinity. And so now I have a polyhedron, an ideal polyhedron in this hyperbolic space that has geodesic sides and vertices on the boundary of hyperbolic space. And now I have several ways of triangulated into tetrahedron. And each way of the triangulated gives me an expression for this matrix element that I'm computing. And the fact that they are the same is following from the pentagonal identity for the dilogarithm. So it's kind of non-trivial but surprising and pleasant calculation. And so far we're able to establish this for this case where we have 5 vertices. But we believe that it shouldn't be too hard to prove that this is true in general. So if I have now I'm taking the product of say n fields, and then I look at the corresponding matrix element, I can write it in terms of products of a smaller number of fields, and the fact that all these possible ways of writing as a product are equivalent depends on the various triangulations of this polyhedron with many vertices into tetrahedron, into hyperbolic tetrahedron. So we believe this is a natural extension of the notion of vertex algebra, though we are still a little bit waiting to formalize it, to axiomatize it in full detail, just because this is the only example that we have. So we're waiting for example. I'll stop here. Thank you.
Any questions? Okay, let's thank our speaker again.